The difference is this. So you will have maximum stress, and this will be equal to P over A, okay, bracket 1 plus by EC over R squared. Okay. Then you have secant, and then you have another bracket. I want you to use a different formula. So on. Then you have pi over 2, okay, square root P over PCR. Okay, you can see that the formula is different already. Okay, you can see that the formula for centric and eccentric buckling are not the same anymore. Okay, so in eccentric buckling, right? So the we will have a factor of safety, okay, for eccentric. So factor of safety will be equal to P max over P applied. Okay. So over here, what we calculate, if this is stress max, okay, what we calculate over here is also equal to our P max. Okay, what we calculate is also for P max. The only thing that's similar regarding eccentric and centric buckling is for this case, PCR is still equal to pi squared EI over LE squared. Okay, and the test that we do, right, we have to test, is the structure safe or is the structure not safe? Okay, so the test, you have to ensure that the stress max has to be less than the stress yield. Okay, so you can see that the difference is the testing. Okay, the testing is different. Okay, and also down here the stress max is different. Well, stress critical is P critical over area. Your stress max is P over A, and you have bracket 1 plus by EC over R squared secant pi squared P over PCR. Now, in our eccentric buckling, I want all of you to use this formula. Okay, it will make your life easier. I repeat again, it will make your life easier. Okay, now it is relatively important that if we are going to apply a formula like this, okay, it's important we also understand how this have been developed. Okay, so we are going to spend maybe 20 minutes or half an hour to derive this. Okay, to derive this. So we are going to use this diagram now. I'm going to use this diagram. Okay, and then we are going to look at the moment at point Q. Okay, so at point Q, so before I go into point Q, this is still our Y, and this direction is our X. Okay, so at point Q, right, the moment is equal to minus PE minus P Y max. Y minus because it's going in the clockwise direction. Okay, it's going in the clockwise direction. That's why it is minus. Okay, so after that, I'm going to write this. This can be also be, rather than always writing Y max, I'm going to write minus P E minus PY. Okay, so this is our equation number 1. And like before, we are also going to apply the elastic curve theory. We specify that EI d squared y over dx squared will be equal to minus PE, or I'll write this equal to moment, and you'll change to moment at point Q, please. So over here, moment at point Q. So we have moment at point Q, which is equal to minus PE minus PY. And then when we rearrange this, we have d squared y over dx squared is equal to minus PE over EI minus PY over EI. Okay. Then rearrange this. So therefore, d squared y over dx squared plus by py over ei, and this is equal to minus pe, okay, minus pe over ei. Okay. So from here, we are going to let, okay, small p squared is equal to p over ei. Okay. So can you write down that we are going to write our, this is our equation number 2. Okay. So from here, we have d squared y over dx squared plus by small py, okay, is equal, or small p squared y minus p squared e. Okay. So this is our equation number 3. So now equation number 3 is a non-homogeneous equation. Okay. So one of the boundary condition, oh sorry, one of the general solution, but we know that it's going to be complex conjugate roots. Okay. So the general solution, okay, will be y as a function of x is equal to a sine dx plus by b cos dx. And because it's not equal to 0, we have to put minus e down here. So this is one of the general solution. Okay. So from here, we are going to have boundary condition. Okay. So this is where x is equal to 0, right? Y is also equal to 0. At the other end over here, when x is equal to L, we have y is equal to 0. Okay. So this case is simulate that both ends are pinned. Okay, both ends are pinned, because over here, why I say both ends are pinned, because over here the theta is not equal to 0. Likewise over here, the theta is not equal to 0. So when that's the case, both ends are pinned. Okay. So coming back to here, we're going to substitute when x is equal to 0, y is equal to 0 into equation number 4, right? So this will be equal to 0, and this will be equal, sine 0 is 0, cos 0 is b, and then you have minus e. So therefore, the constant b is equal to e. So then we write y as a function of x is equal to a sine px plus by e cos px minus by e, and this I will call it equation 4a because it's derived from equation 4. Then the next thing that we're going to do, we're going to substitute our next boundary condition when x is equal to L, right? Y is equal to 0. And we're going to substitute into our equation now, which is equal to 4a, right? So this is equal to 0 a sine PL plus by E cos PL minus by E. Okay. Then we will move things around. So we have A sine PL, and this will be equal to E minus E cos PL. And if we were to rewrite this slightly, gather the terms of the eccentric E is equal to 1 minus cos PL. Okay, and this is our equation 5. Okay, so just to quickly remind, E is the eccentric distance of the axially applied load. Okay, just in case we could not remember. So what we have to do now is we want to determine the constant okay. We want to determine the constant A. Okay. So now, in order to determine the constant A, we are going to apply double angles. And we know there's a relationship where we have sine 2 theta is equal to 2 sine theta and cos theta. Okay. Then we are going to let, right? We are going to let 2 theta will be equal to our PL. And this in terms will get theta is equal to PL over 2. Okay. So now, by knowing this, we know that therefore sine 2 theta is equal to what? Sine PL. And this will be equal to 2 sine PL over 2. And then cos PL over 2. Okay. And this is our equation number 6. And the one we have, this is equation number 7. So why we do this is now we can have a relationship of sine PL over here. And we also can have sine, okay? So this later on, we will equate them later on, okay? And then the next one we're going to have, we're again going to use, we're going to apply another double angles. Okay, so now is we have cos 2 theta is equal to 1 minus 2 sine squared theta. Okay, so we know that 2 theta is equal to PL, right? So therefore, 2 theta, we going to put in cos PL, okay, minus 1, not minus, equal to 1 minus 2 sine